So far, we've been integrating equations like y is equal to f of x, and we call these Cartesian equations. They could instead ask us to integrate parametric equations. So here's an example question that I wrote on this, where we're told about a curve C that is defined by the parametric equations x is equal to t squared minus 1, y is equal to t squared minus t for when t is bigger than or equal to 0. And we need to find the shaded region R that is bound between the curve C, the x-axis, and the line x is equal to 3. So R is this region here. Questions on parametric integration will always be revolved around area. So what's the difference between this question and the other area questions we've tackled so far in integration? Well, let's approach this question how we would normally do with integration questions. So to find this area R, what we would normally do is we would integrate between the lower limit, which we can see here is 0, and the upper limit, which as this goes up to x is equal to 3, the upper limit is going to be 3, and this is for y over dx. So this is how we would normally approach it. Now, there are two problems with this here. The first one is normally y is a function of x. Remember, this dx here means we're integrating in terms of x. Now, normally this is fine because normally y is a function of x, so this works well when we're integrating. The issue with parametrics is y is no longer a function of x. We can see because it's parametric that y is now a function of t. So if we sub in this y here, we get that it's now the integral between 0 and 3 of this t squared minus t for dx. And the problem with this is we are integrating here because it's dx, we're integrating in terms of x, but we don't have x terms here, we have t terms. We don't want this to be a dx, we want this to be a dt. Now luckily there is a way that we can solve this. What we can do is we can differentiate this x parametric equation here, this x is equal to t squared minus 1. So what we can do, if we differentiate this, it's going to be dx over dt, and this is equal to, so if we differentiate this here, if you differentiate t squared, this is equal to 2t. This is just year one differentiation. And if you differentiate minus 1, this is just a constant, so it goes away. So dx over dt is equal to 2t. If you multiply both sides by dt, so you get rid of this dt denominator here, you get dx is equal to 2t dt. I will just note here, to get from this equation to this equation, multiplying both sides by dt is not actually mathematically how it works, but I think it's fine to think about it like that at A level. So we have this dx is equal to 2t dt, and what's useful about this is we now have dx as the subject, and we can now sub out this dx here for this 2t dt. So this becomes the integral between 0 and 3 of this t squared minus t multiplied by, instead of dx here, this 2t dt. And this is useful to us because this is now a dt and all of these are now t terms. So we've solved the first problem. Okay, so we've solved the first problem, but we have another issue here, and it's to do with these limits of 0 and 3. So these limits are in terms of x. So here x is equal to 0 and x is equal to 3. Remember, we got them by looking at the x-axis on this graph here and seeing they're at 3 and 0. The problem with this is we're now integrating in terms of t, and therefore the limits also need to be in terms of t, not x. Now, the way that we can solve this is by using the x parametric equation here, this x is equal to t squared minus 1. And what we can do is we can sub in these limits for x as 3 and 0, and then rearrange in order to find their corresponding t values, and then just use these as the limit, okay? So if we start with the x is equal to 3, so if we sub this in as x here, we'll get that 3 is equal to t squared minus 1, and then we're going to rearrange in order to make t the subject here. So move this minus 1 to the other side, so we get that 4 is equal to t squared, and then if we square root both sides, we get that 2 is equal to t. Just note that usually when we square root, we have to consider the plus and minus square root. However, in this question, we're told that t is bigger than or equal to 0. So therefore it's going to be the positive root. So t is equal to 2. So this here is the upper limit. And then to get the lower limit, this x is equal to 0. We're going to sub in x is equal to 0 here and then rearrange in order to find the corresponding t value. So here 0 is equal to t squared minus 1. To move this minus 1 to the other side, so we get that 1 is equal to t squared. The square root both sides, so 1 is equal to t. So this is the lower limit. So therefore this integral becomes the integral between 1 and 2 of this function here. And now we have solved the two issues and we can actually go about integrating this. Okay, so if we go about integrating this, so firstly we have this t squared minus t multiplied by this 2t. So if we expand this, so t squared multiplied by 2t is equal to 2t cubed, and minus t multiplied by 2t is equal to minus 2t squared, like this here. So to integrate this, we have these two terms, so let's consider them individually. So if we start with the 2t to the power of 3, I've taken the 2 out of the integral like this here. So when you integrate t to the power of 3 is equal to 1 over 4t to the power of 4. This is just year 1 integration. Times it by the 2 that we took out at the start, so this is equal to half t to the power of 4, like this here. And then if we integrate the minus 2t squared, again I've taken the minus 2 out of the integral. When you integrate t squared, it's equal to 1 over 3t to the power of 3, and multiply this by the minus 2 we took out at the start, so it's equal to minus 2 over 3t cubed. So if you add these terms together, you get that this integral is half t to the power of 4 minus 2 over 3t to the power of 3. So now we need to sub in the limits of 2 and 1, which is what I've done down here. And if you put this here into a calculator, you get out a value of 17 over 6. So this here is the area of R. And that's how you do parametric integration. There's not really much more to it, so I'm just going to go straight into exam questions after this. So in order to do parametric integration, you write out the integral as normal, as I showed at the start, and then you sub out the dx for dt like we did here, and then you change the limits from being in terms of x to being in terms of t. Okay, so now we'll go through some past exam questions. So for this one here, we're told about a curve that has the parametric equations x is equal to 6 sin t, y is equal to 5 sin 2t, and we're also given the domain of t between 0 and pi over 2. And we're told about a region R that lies underneath this curve, and for the first part we need to show the area of R can be given by this integral here. Okay, so let's set up the initial integral. So it's going to be the integral between, so we can see the lower limit is 0 as it starts at the origin, and the upper limit is this x-intercept, this root. Now we don't know what this is, we're not given it, so at the moment we're just going to call this a. So we'll say that the upper limit is a, and then y is this 5 sin of 2t, and then at the moment it's dx. Okay, so remember the two problems of this. Firstly, we need to replace this dx, and the way that we're going to do this is we're going to differentiate the x parametric equation. So it's going to be dx over dt is equal to 6, and then if you differentiate sin t, remember it's cos t, and then if you multiply both sides by dt, we get that dx is equal to 6 cos t dt. So we can sub out this dx here for this 6 cos t dt like this here. We can simplify this because 5 multiplied by 6 is 30. So we have the integral between 0 and a of 30 sin 2t cos t dt. Okay, now if you look at the final answer that we need, it's 60 sin t cos squared t, and the big difference is here we have this 2t, whereas here you can see that both of the trig functions don't have a 2t in them, they're both just t. So this is a sign that we need to get rid of this 2t and that we need to use the double angle formula. So go back to the videos on the double angle formula if you need a reminder of it, but the double angle formula for sin of 2t is 2 sin t cos t, so therefore we can sub out this sin 2t here for this, so it's going to be 30 cos t multiplied by this, and then instead of sin 2t here we have this 2 sin t cos t 30 multiplied by 2 is 60, and cos t multiplied by cos t is cos squared t. And this is what is inside this integral here, this 60 sin t cos squared t. Okay, so we found the bit inside the integral. Now what we need to do is find a, and we're told in the question that a is pi over 2, so we just need to prove this. Now a is the root of the curve, so remember roots are where y is equal to 0. So what we're going to do with this parametric equation here, we're going to set y equal to 0 like this here. So 0 is equal to 5 sin of 2t, and we're going to rearrange in order to find t, and this will be the value of a. So divide both sides by 5, so we get that 0 is equal to sin of 2t. Now, sin is, if you look at a sin graph, sin is 0 at 0, pi, 2 pi, at 3 pi, and so on. So that means that 2t is equal to either 0 pi, 2 pi, 3 pi, etc. Now, it needs to be in this domain here between 0 and pi over 2. Now, if we divide everything by 2 here, to get rid of 2 on this side, we get that t is possibly equal to 0 pi over 2, pi, 3 pi over 2, and so forth. And we can see that there are two values that lie in this domain, which is 0 and pi over 2, because we have the equal inequality signs here, so it can be equal to 0 and pi over 2 as well. And 0 is this root here, and pi over 2 is this root here. So therefore, a is equal to pi over 2. So therefore, we've solved the first part. Okay, and then for the second part, we need to show that the area of R is 20. So essentially what we just need to do is integrate this here and show it's equal to 20, okay? So if we first focus on integrating this function here, this 60 sin t cos squared t, I've taken the 60 out of the integral here, so we're focused on integrating this sin t cos squared t. Now to integrate this, there's a couple of ways that you can do it. You can use substitution, but I think the easier way to do it is using the reverse chain rule. Now we did a video on the reverse chain rule in the integration chapter, so go back to that if you need a reminder of how it works. But with the reverse chain rule, there are essentially two clues for when you can use it. The first one is if there's either a power or a fraction in the integral, and you can see that we have this power of 2 here, so this is the first clue. And the second clue is whatever is inside the power, so in this case inside the power of 2 is this cos t. If you differentiate it, this function is also present in the integral. When you differentiate cos t, you get minus sin t, and you can see that sin t is also present in this integral. So these two clues show that we can use the reverse chain rule. Now when we do the reverse chain rule, we focus on this cos squared t and we raise it by 1, the power, so now it's cos cubed t, and we differentiate this. Now to differentiate cos cubed t, it might be easy to see this if we write it as cos t to the power of 3 like this here. To differentiate this, we're going to use the chain rule. Now the way that I talked about in that video, I say that the chain rule is the inner function differentiated multiplied by the outer function differentiated. For cos t to the power of 3, the inner function is cos t and the outer function is this power of 3 here. So the chain rule is the inner function differentiated, so cos t differentiated. As I've already mentioned, when you differentiate cos t, you get minus sin t, like this here. And this is multiplied by the outer function differentiated, so this power of 3 differentiated. If you think about x to the power of 3, when you differentiate this, it becomes 3x squared, so it works a similar way to that. So the 3 comes down as the coefficient. This cos t, we don't touch it, we kind of treat it as the x, we don't touch it, so it remains like this, and now it's going to be to the power of 2 instead. So this is what happens when you differentiate cos cubed to the power of t. It becomes this here, and we can simplify this because we have this minus here and we have this 3 here, so this is going to become minus 3 sin t cos squared t, okay? And what you can see is this sin t cos squared t is what we have here, so therefore this shows that this here is the correct integral, this cos t to the power of 3. But one thing we also do with the reverse chain rule is we also divide by this coefficient here, minus 3. So therefore it's going to be minus 1 over 3 cos cubed t. So it's this here divided by this coefficient of minus 3. Remember to times it by 60 because this is what we took out at the start. So this is the integral here. Okay, so we have 60 multiplied by this minus 1 over 3 cos cube t, which will simplify down to minus 20 cos cube t, like this here. So therefore now we're going to plug in the limits of pi over 2 and 0, which is going to be like this here. And if you put this into your calculator, this is equal to 20. Okay, so here's another example question where we're told about the curve C with parametric equations x is equal to the natural log of t plus 2 and y is equal to 1 over t plus 1. And this is for when t is bigger than minus 2 over 3. And for part A, we need to state the domain of values of x for the curve C. So we essentially just need to find the values of x that we can use in C. Now, we talked about questions like this back in the parametric equations video back in year 2 of chapter 8. The way that we tackle questions like this is we're going to consider this parametric equation here 4x over this t is bigger than minus 2 over 3. As we need to find the possible x values that we can use, what we're just going to do is consider the range of values that the natural log of t plus 2 gives out for this inequality here. This t is bigger than minus 2 over 3. So if we consider this t is bigger than minus 2 over 3, so here we have t plus 2, so that means that in this case t plus 2 is going to be bigger than 4 over 3. I've just added 2 to both sides here. So if we consider the natural log of t plus 2, the smallest value that this is going to have is the natural log of 4 over 3. If we increase t plus 2, so we increase 4 over 3, the natural log is just going to get bigger. So that means that the natural log of t plus 2 is going to be bigger than the natural log of 4 over 3. So this is going to be the smallest value that it can have. And you can see that x is equal to the natural log of t plus 2. So if we just sub this out for x, we get that x is bigger than the natural log of 4 over 3. And this here is the final answer. This is the domain of values of x for the curve C, where it's bigger than the natural log of 4 over 3. Okay, and then for part B, it starts talking about this region R here that is bound by the curve, the x-axis, and the line x is equal to the natural log of 2, and the line x is equal to the natural log of 4. And we need to use calculus to show that the area of this region R is the natural log of 3 over 2. So let's set up the integral as we normally do. So this is going to be the integral between, so the lower limit in terms of x is going to be this natural log of 2, and the upper limit is going to be this natural log of 4, and then y here is this t plus 1 under 1. Then at the moment we're integrating in terms of x. Now remember the two things that we need to do here. Firstly, we need to replace this dx for a dt, and secondly we need to rewrite these limits here in terms of t. So if we first focus on subbing out this dx here, so we need to differentiate this x is equal to the natural log of t plus 2, so this is going to be dx over dt is equal to, and then remember when you differentiate a natural log it becomes 1 over like this here, so it's going to be 1 over t plus 2, and then if we multiply both sides by dt we get that dx is equal to 1 over t plus 2 dt. So we can sub out this dx here for this 1 over t plus 2 dt like this here. And now we need to rewrite these limits here in terms of t, not x. So what we're going to do, but at the moment both of these are in terms of x, what we're going to do is sub them into this parametric equation here for x and then rearrange to find their corresponding t value. So if we start with the natural log of 4, it's going to be the natural log of 4 is equal to this natural log of t plus 2, so this means that 4 is equal to t plus 2. Move the plus 2 to the other side, so we get that t is equal to 2. And then this one here is going to be the natural log of 2 is equal to the natural log of t plus 2, so 2 is equal to t plus 2. Move the plus 2 to the other side, so we get that t is equal to 0. So in terms of t, these limits here are 2 and 0, and now we have this integral here that we can start to work with. Okay, so now we need to go about integrating this function here, this 1 over t plus 1 multiplied by 1 over t plus 2. Now we can rewrite this like this here, where it's 1 over t plus 1 t plus 2. Now this here we cannot directly integrate, however we've talked about how to integrate functions like this in the integrating using partial fractions video. So go back to that if you need a reminder, but this here we're going to split this up into two partial fractions, one with this denominator of t plus 1 and one with this denominator of t plus 2, and we're going to call the numerators a and b, and these are constants that we need to find. So the first step is we need to multiply everything in this equation here by this denominator. So we're going to multiply everything by t plus 1, t plus 2, these two brackets here. So these two brackets will cancel out with the two brackets in this denominator, just leave us with the one numerator on this side. And then this t plus 1 bracket will cancel out with this t plus 1 denominator to leave us with a multiplied by t plus 2. And then this t plus 2 bracket will cancel out with this t plus 2 denominator to leave us with b multiplied by t plus 1, like this here. Okay, now from here there's two ways to solve for a and b. You can either use substitution or you can compare coefficients. I always use substitution because I think it's a lot easier. So if we first focus on this bracket, this t plus 2, if we sub in t is equal to minus 2, this bracket will be equal to 0, so therefore this term here will cancel out and just leave us with 1 is equal to b. And then if we sub in t is equal to minus 2 here, we will have minus 2 plus 1, which is equal to minus 1. So this is going to be that 1 is equal to minus b, so therefore b is equal to minus 1. And then if we focus on this bracket here, if we sub in t is equal to minus 1, this bracket will be equal to 0, so this term here will cancel out and just leave us with 1 is equal to a. And then if we sub in minus 1 here, it's going to be minus 1 plus 2, which is equal to 1. So this is going to be that 1 is equal to 1a here. So a, so therefore 1 is equal to a, like this here. So therefore if we sub these a and b terms into this here and into this integral, it's going to be the integral between 0 and 2, but instead of writing it like this here, we've written it like this, where it's 1 over t plus 1 minus 1 over t plus 2. Okay, so if we go about integrating this here, this 1 over t plus 1 minus 1 over t plus 2, we have two terms, so let's consider them individually. If we start with the integral of this 1 over t plus 1, now to integrate stuff like this is the stuff that we talked about in the integrating f of ax plus b video. So when we integrate 1 over something, remember something like 1 over t is equal to the natural log of the modulus of t, okay? So that's what the answer is going to be. It's got this t plus 1 here, so it's going to be the natural log of the modulus of t plus 1. The only difference with things like this is we need to divide by the coefficient of t. However, because the coefficient of t here is 1, it doesn't make a difference. We don't need to divide by anything. If, for example, it was instead 1 over 2t plus 1, this would instead be a half of the natural log of t plus 1 because we divide by 2. However, we don't have a coefficient for t here. And then if we consider the integral of this minus 1 over t plus 2, I've taken the minus out of the integral like this here. This is the exact same thing, so it's going to be the natural log of the modulus of t plus 2. There's no coefficient in front of the t here, so we don't need to divide by anything. This plus 2 and this plus 1 here doesn't make a difference, except from the fact that it's different in the natural log, and we have this minus in front of the natural log here. So therefore, if we add these terms together, it's going to be the natural log of the modulus of t plus 1 minus the natural log of the modulus of t plus 2, and then plus c on the end. And we can simplify this because remember, when you minus a log from a log, you can divide what's inside. So this is going to be the natural log of the modulus of t plus 1 over t plus 2, and then we've got this plus c here. So now we're going to sub in the limits of 2 and 0. So that's what I've done here. So it's going to be the natural log of 2 plus 1 over 2 plus 2 minus the natural log of 0 plus 1 over 0 plus 2. 2 plus 1 is 3, 2 plus 2 is 4, 0 plus 1 is 1, and 0 plus 2 is 2. So it's going to be this here, the natural log of 3 over 4 minus the natural log of half. Again, when you minus a log from a log, we can divide what's inside the logarithm. So this is going to be the natural log of 3 over 4 divided by half. Remember, when you divide by a fraction, it flips it. So this is now going to be times 2, like this here. 3 over 4 times 2 is 3 over 2. So this is the natural log of 3 over 2, which is what's required. So this is the area of R. Okay, so here's one final exam question on parametric integration. Okay, so we're shown this sketch here that is of the curve with parametric equations x is equal to 8 sin squared t and y is equal to 2 sin 2t plus 3 sin t, and it's for this t domain here between 0 and pi over 2, and we're told about a region R that lies underneath the curve and is bound by the x-axis and the line x is equal to 4. And for part A, we need to show that the area of R can be given by this integral here. Okay, so let's set up the original integral. Okay, so it's going to be the integral between, so the lower limit is going to be 0 and the upper limit is going to be 4, and y here is equal to this 2 sin 2t plus 3 sin t, and at the moment this is for dx. So remember the two things we need to do. Firstly, we need to sub out this dx for a dt, and the way that we're going to do this is differentiate this parametric equation. So it's going to be dx over dt is equal to 8 multiplied by, and then we're going to differentiate sin squared t. Now the way that we're going to do this is by using the chain rule. It might be easier to see this if we write this as sin t to the power of 2 like this here. The inner function is sin t and the outer function is the power of 2, and the chain rule is the inner function differentiated multiplied by the outer function differentiated. So the inner function differentiated is this sin t differentiated, and remember when you differentiate sin you get cos, so this is going to be cos t, and then this is multiplied by the outer function differentiated, which is this power of 2 differentiated. When you differentiate a power of 2, the 2 comes down as the coefficient like this here, so it's 2. Remember, we don't touch the inner function when we differentiate the outer function, and now it's going to be to the power of 1 instead, and we can simplify this because 8 times 2 is 16, so this is going to be 16 sin t cos t. Okay, and if we multiply both sides by this dt, we would get that dx is equal to 16 sin t cos t dt. So therefore we can sub out this dx here for this, so it becomes the integral between 0 and 4 of this 2 sin 2t plus 3 sin t multiplied by this here instead of dx, this 16 sin t cos t dt. Okay, so we have this integral here, and we can simplify this because we have this 2 sin 2t multiplied by this 16 sin t cos t. 2 times 16 is 32, so this is going to be 32 sin 2t sin t cos t. And then we multiply these two terms together. 3 times 16 is equal to 48, and then sin t times sin t is equal to sin squared t like this here. And we have this cos t at the end. Now, if we look at the integral that we want as our final answer, we have this 48 sin squared t cos t, which is what we have here. So this is fine, we don't need to touch this. The issue is this term here, which we don't have in the final answer. We have this 8 minus 8, and then we have this cos 40. If you consider the double angle formula for cos 40, if you consider the sin version, it's this here, where cos 40 is equivalent to 1 minus 2 sin squared of 2t. Now we kind of want this 2t here because then we can sub it out for this cos 40. So this sin 2t is fine. The issue is this sin t cos t here. But what we can do with this is, if you consider the double angle formula for sin 2t, it's equivalent to 2 sin t cos t, and you can see that we have this sin t cos t that we have here. For this identity, if you divide both sides by 2, you get that half sin 2t is equal to sin t cos t. So what we can do is we can sub out this sin t cos t here for this half sin 2t. So that's what I've done here. So it's become this 32 sin 2t multiplied by half sin 2t. And we can simplify this because 32 times a half is 16, and sin 2t multiplied by sin 2t is sin squared 2t, like this here. Okay, So we have this term here. Now, if we look at this identity down here, let's make this sin squared 2t the subject. So let's move this 1 onto the other side. So it's cos 4t minus 1 is equivalent to minus 2 sin squared 2t. And if we divide both sides by minus 2, it will become a half minus a half cos 4t is equal to this sin squared 2t. So what we can do is we can sub out this sin squared 2t here for this half minus half cos 40. So that's what I've done here. So we have this 16 at the front, and then we've subbed out this here for this half minus half cos 40. 16 minus a half is 8, and 16 minus a half here is also going to be 8. So this is going to be minus 8 cos 40, like this here. And you can see that this is the terms that we want here, this 8 minus 8 cos 40. So this is what we can sub in for this here. Okay, so we have the correct function here inside the integral. Now we need to do the second step, which is when we replace these limits. At the moment, remember, these are in terms of x. We need to get them in terms of t, and the way that we're going to do this is sub them into this parametric equation here and rearrange in order to find t. So let's start with the x is equal to 0, so it's going to be 0 is equal to 8 sin squared t, so that means that 0 is going to be equal to sin squared t. Square root both sides, so 0 is equal to sin t, so that means that t is equal to 0, so the lower limit is still t is equal to 0. Then the upper limit x is equal to 4, if we sub this in, so it's going to be 4 is equal to 8 sin squared t, so that means that if you divide both sides by 8, a half is equal to sin squared t. Square root both sides, so that means that 1 over root 2 is equal to sin t. You don't need to worry about the plus or minus here, because in this domain between 0 and pi over 2, sin t cannot be negative, so it has to be positive. And therefore, if you do the inverse sin of this 1 over root 2, you get that t is equal to pi over 4. So this is the upper limit. So therefore, this value of a here, this upper limit, is pi over 4. This is the integral for part A. Okay, and then for part B, we actually need to go about integrating this in order to find the exact area of R. Okay, so in order to integrate this, let's first integrate this function. So we have 3 terms, so let's focus on these 3 terms individually and integrate them. If we integrate a, this is easy. If you integrate a in terms of t, it's going to be 8t. If we then focus on integrating this minus 8 cos 40, I've taken the minus 8 out of the integral like this here. If we integrate cos 40, we've talked about how to integrate this in this chapter already. When you integrate cos, you get sin, so it's going to be sin 40, but you also need to divide by the coefficient of t, which in this case is 4, so it's going to be 1 over 4 sin 40. When you integrate cos 40, we need to multiply it by the minus 8 we took out the start, so minus 8 multiplied by a quarter is minus 2. So this is minus 2 sin 40, and then if we integrate this 48 sin squared t cos t, so I've taken the 48 out of the integral like this here, so we need to integrate sin squared t cos t. We need to use the reverse chain rule for this, as I've already talked about in this video. The 2 clues is 1, if there's a power or a fraction present. We have this power of 2 here. Remember, the second clue is the function that's inside the power, so in this case sin, if its differentiated form, is also in the integral, and when you differentiate sin you get cos, and this is also present. So these are the signs that we need to use a reverse chain rule. Increase this power by 1, so it's going to be sin t to the power of 3, and then we're going to differentiate this. So we're going to differentiate this using the chain rule, with the inner function being sin t and the outer function being the power of 3. So remember, the chain rule is the inner function differentiated multiplied by the outer function differentiated. So the inner function differentiated is sin t differentiated. When you differentiate sin, you get cos, this is cos t. Then the outer function differentiated, this is power of 3 differentiated. So when you differentiate a power of 3, the 3 will come down as a coefficient, it's going to be 3. You don't touch the inner function when you're differentiating the outer function, this is still sin t, and now it's going to be to the power of 2 instead. So this is going to be 3 sin squared t cos t. When you differentiate this, this is of the correct format, this sin squared t cos t. that we have in the integral. So this suggests that this is the correct answer, but remember you also need to divide by this coefficient here, which is 3. So when you integrate sin squared t cos t is equal to 1 over 3, because we need to divide by the 3 of this sin cubed t. Multiply it by the 48 that we took out at the start. 48 times 1 over 3 is 16. So when we integrate this here, this is equal to 16 sin cubed t. So therefore, this entire integral is these three terms added together. Okay, so this here is the answer to the integral, this 8t minus 2 sin 4t plus 16 sin cubed t plus c. And now we need to sub in these limits of pi over 4 and 0, which is what I've done down here. And we can do some simplifying here. So 8 times pi over 4 is 2 pi. This term here, so we have 4 times pi over 4, which is pi. So this is sin of pi, and sin pi is 0. So this term will just cancel out. This term here, so sin of pi over 4 is equal to root 2 over 2. So this is going to be 16, and then this root 2 over 2 cubed, like this here. This term here is 8 times 0, so this will cancel out and be 0. This term here, so 4 times 0 is 0, and sin of 0 is 0, so this term will cancel out. And this term here, we have sin 0, which is 0, so this term will cancel out as well. So we're just left with this here, and we can do some simplifying. Here we have root 2 over 2 to the power of 3, so this is going to be this here. We can simplify this because root 2 times root 2 times root 2 times root 2 is going to be 2 root 2, and 2 times 2 times 2 in the denominator is going to be 8, and then 2 root 2 over 8, this 2 will cancel out with this 8 here to leave us with root 2 over 4 like this here, and 16 times root 2 over 4 will cancel out this 4 here and leave us with a 4 like this. So the final answer here in its simplified form, the exact area of R is 2 pi plus 4 root 2.